Hi you guys, my name is Stephen, and on behalf of myself and my sound guy Carl, I'd like to welcome you to my Calibration channel. I have 30 years experience working in facility maintenance operations, mostly in biotechs and biopharma production facilities. 10 of those years I spent carrying a bag as a calibration technician. Afterwards, I continue to be interested in the theory of calibration and the way it's practiced day to day in a workplace. This video is about an idea that I first encountered while reading an article written by Dan Collins. Dan was writing about how to improve the reliability of control loops, but I think his idea has far-reaching implications well beyond the scope of his article. So I hope you will stick with me while I describe it to you. To start off, let's talk about some basics. Here we have a schematic rendered on some very, very expensive software that I acquired for representing graphics. It just shows a very simple control loop. And for those of you who are not familiar with that, this is the same kind of approach you could see in the furnace controls in your hallway in your house, or in the hearing aids that I wear. In this case, we see a control loop. Let's say it's a method for controlling the temperature in a 10,000 liter vessel. It looks quite simple, but I have seen many renderings in real life of control loops that look exactly this simple and work very well. So what we have is an appropriate temperature sensor that's sitting in the process that we want to measure, and it talks directly to a PID controller. And PID just means proportional, integral, and derivative control. These are generic off-the-shelf microprocessors that run many processes throughout the industrial and domestic installed base. In keeping with my focus on calibration and instrumentation, let's look at the most likely failure modes for the temperature sensor itself. The first one is a catastrophic failure. Let's just say you're up in the control room watching this process run in this 10,000 liter vessel, and it's held a temperature of 50 degrees for the last hour, because that's what's in the set point. All of a sudden, the temperature display goes to 0 degrees, or 114 degrees, or some other kind of nonsense. Now, you know it's nonsense because you can't change 10,000 liters of fluid that fast. So the chances are very good that what you just witnessed was a catastrophic failure of the temperature probe itself. The next failure mode is one that might be quite a bit more difficult to identify, even if you were sitting there watching it. This is a change in the dynamic response of our sensor. So that just means that instead of responding quickly to small changes in the temperature of this vessel, it takes a lot longer for it to register those changes, even if eventually it proves to be just as accurate as it was before. This could wreck the chemistry of the process you're running in the vessel. I might say that pH probes and dissolved oxygen probes are particularly vulnerable to this kind of failure. The last failure mode I want to talk about is what's called OOT. And calibration techs the world over will recognize that acronym. It stands for out of tolerance. So let's just say you've come out to this vessel on a regularly scheduled basis several times, and every time you do, you pull the probe out of the process, you put it in an oil bath with a much more accurate standard, and you compare the two. Every time up till now, there's been a disagreement of no more than 1 degree. As long as that holds, you're cool, because that's the tolerance for your probe and your process. Yesterday you came out and you discovered instead of a 1 degree difference between the two probes, you found a 3 degree difference. Okay, you're out of calibration, and your process is out of tolerance. This is some very bad news for the process owner. And to make it worse, you probably can't tell them when it first happened unless you luck out and have another data stream that can give you some clues. Otherwise, you have to conclude that the last time this process was in calibration was the last time you did the cal, and it failed 1 second after you walked away. Well, when was that? Could have been 6 months or a year ago. So, as I said, this is very bad news for the process owner. He may be looking at a product recall. He certainly is looking at having to figure out how many batches he's going to have to discard. This could mean thousands or even millions of dollars worth of product. Okay, so let's contrast that situation with the proposal that Dan has. I, again, have rendered it in some extremely expensive graphics software, and here's my rendition of Dan's idea. It's actually quite simple. He says instead of running one probe in your process, run two. But instead of running the sensor data right straight to the PID controller as you did before, you run it through a black box where it's subjected to some very standard statistical analysis. Now, this is a black box. It's not black magic. The tools that Dan suggests are used every day in many, many different industries. In addition, in Dan's article, he uses control charts to plot the performance of his two sensors compared to each other. And here's the world's simplest control chart, just to show you what's going on. Dan calculated upper and lower control limits for his two data sets, and as long as the data doesn't exceed one of those limits, we can be sure that we're not seeing one of the failures that I described earlier. So how does Dan defend his ideas? He certainly didn't go out and buy two 10,000-liter vessels, run one with one probe and run another with two probes, and then compare them to see which one performs better. Instead, he went to Excel and he said, hey, Excel random number generator, give me 500 points that orbit around 100 degrees centigrade, that vary only a half a degree or less, and draw them from the normal distribution. And having done that once for sensor A, he does it again for sensor B. So now he has two data sets that simulate the data that might come from this block diagram if you were trying to hold 100 degrees centigrade in a vessel. Then what Dan does next is very clever. He starts adding very, very small error elements to the sensor B data. He starts out small and he makes those errors incrementally bigger and bigger. What he's trying to do is test the sensitivity of his approach. And I was convinced, and as I think you will be if you read his article, that this approach is actually quite sensitive and very much deserves to be looked at by many process owners in many different business sectors. As I said, Dan's ideas only take up 6 pages in a magazine article, including the illustration, so I heartily recommend you go read it for yourself. So the last thing I want to do in this first video is talk about the downsides to Dan's approach, and there are some definite downsides, especially within pharma. Let's take them in order. First is the cost of the probe itself. Second is the cost of the calibration of that probe. Third is the cost of transposing Dan's idea from a magazine article into code that our PID controller could recognize and act on. The fourth cost and the fourth downside to Dan's idea is the biggest one, and the one with political heartaches, I think. And that's the cost of validating this process. So in the next video, I will get into the details of each of those downsides, as well as the upsides for Dan's approach that I think you'll want to stick around for. I think they're very thought-provoking and interesting. In the meantime, thank you for paying attention. On behalf of my makeup guy, Carl, and myself, I want to wish you a good day. Thank you.